My name is Arun Lakhotia. I'm a professor here at CMIX, and I have a great pleasure of bringing to you all Dr. Mark Harman as our distinguished speaker today. Mark and I, it's a long, old collaboration. We're in the same space, software engineering, broadly speaking, more so helping programmers develop better program faster, better, and so on. Mark has the distinction of having created a field of study, because I think that's an incredible thing. This area called search-based software engineering. Yes, I think he's the pioneer. And I have to first sort of confess, I'm not, when I started, at least at then, I was not a big proponent. I didn't think all of this search and AI and so on, it's good, but it's not going to go nowhere. It is like, there's good stuff, but not something that I could associate. I'm a very algorithmic thinker. And turns out I've been proven wrong. And now we have ChatGPT, and Mark has done some incredible work of taking his work, research, and move it into Facebook or Meta. And Mark is going to talk about that. So I'm not going to take a lot more time. I really want to give Mark the time to share his experiences and thoughts. And with that, let's do a little, at least virtual clap. You have a little clap sign on Zoom. You can go press the clap button and show your appreciation there. Thanks, Sam. All right, Mark, it's all yours.
Thanks very much, Arun. So I've got an hour, is that right?
Yeah, you have an hour. Yeah.
So I think it's probably best if we break that into two halves. I'll try and talk for no more than about half an hour, and then people can kind of pitch in and ask me lots of questions, if that's okay.
Yeah, that's absolutely.
Yeah, I might, go a little bit over the half hour, but we'll see how we get on. So I'm going to share screen now, so you can see my slides. Okay. So I'm hoping you can now see my first slide. Is that
probably something I'll hate. So
if everyone could mute their microphone, that'd be great. Thanks very much. So yeah, so I'm Mark Harman. I'm going to give a talk today that's based on a keynote talk I gave at a conference recently. What's different is at the conference they didn't have that much. I think they probably had about the same time to ask questions, but I'm sure you'll ask really incisive and interesting questions, and I'm looking forward to that. So I should call out that the talk I'm going to present today is based on work done by a large number of people that I've had the pleasure of collaborating with. All mistakes and content is my responsibility, but the technologies that I'm going to be talking about and the kinds of ideas we've implemented, have been done by a lot of other people. I've played a role in it, but I want to call out the fact that this isn't my work, this is our work. So in today's talk, I'm going to talk about how we do simulation-based testing at Meta. Meta is the company that used to be called Facebook until about November year before last. And I'm going to focus on something that I call the build effort problem, which I'll get into detail, but the TLDR is that it's the time it takes to build the application you're trying to test, or you're trying to understand, or you're trying to improve. And funny thing is, if you look back to the 1970s, the largest systems we had back then took about half an hour to an hour to build, and it's still the same today. Obviously, the systems have gotten orders of magnitude bigger, and the build technology's gotten orders of magnitude better. But somehow there's some sort of spooky constant in software engineering that, build effort always seems, it's never a solved problem, and I think it probably never will be a solved problem. So we need to bear that in mind if we're doing technologies that are going to involve multiple builds, as we'll see. And it sounds like an engineering detail, but it actually turns out to be quite important, I think. And the other thing is the new feature build cost problem, which is, as software engineers, we continue to want to try out new features. Let's see what it would look like with this. And it would be so much better if we could do that really fast with a very rapidly generated prototype. Most of the trends in software engineering methodology research have pushed us into directions where we try to generate stuff much faster as humans. But I think using technology, we can get a few more orders of magnitude out of that. And some of these things tip us over kind of important rubicons. Like, once the cost of building a new feature becomes like minutes, not days, it's not just more efficient. It's like you now change the way you can think about what it means to explore the space of possibilities and what your software can do and how you approach the design of new features. And then I'm going to talk a little bit about how we use simulation together with this concept of mechanism design to scale the approach that's known as genetic improvement. So genetic improvement is where you take an existing software system and you think of the code of that software as just genetic material that can be mutated and tweaked around. And you're guided by tests. So you can't just do any transformation, but you're not guided by static analysis. So the transformations you do don't have to preserve the meaning of the program, then you have to preserve the tests. And that's called genetic improvement. And I'll tell you a little bit about how we've been looking into the problem of how we scale that using this approach of mechanism design. And these techniques apply to software repair, which is a current topic of great interest in the software engineering community. So Aaron mentioned that I was going to be talking to a community of people, including undergraduates all the way through to PhD students and possibly faculty. So I thought I'd just spend 5 minutes telling a little bit about my journey in software engineering. My first encounter with software was writing a game when I was a school child in the 80s, and I had this game called Sword Fight at Midnight. The graphics of which looked nothing like this. In fact, this is what the graphics looked like. This is what passed for game graphics in the early 1980s, and that's what a television set looked like, which was the monitor for computers in those days. So you can see I didn't have much graphic skill, but it got me into computing, and in particular it really made me realize what you could do with code. And then if I wind forward a little bit, after I completed my undergraduate study, I did a PhD at a university that no longer exists and was probably one of the lowest ranked universities in the UK at the time. But I liked it. I felt I got a good education there, and I'm very grateful for it. So I got my PhD. And then I tried to publish the work for my PhD, and I thought I'd tell you that story. And this, I hope, is a heartening story for those of you who are embarked on a PhD program yourself. So I hadn't got any papers out of my PhD. I hadn't published a single paper when I got it. So I decided maybe I should try and publish some of it. So I submitted it to the Computer Journal, and it got rejected. So I thought, okay. Remember, that was 92. So then a year later, there was this conference called Partial Evaluation and Symbolic Manipulation, PEPM. I thought, oh, this is exactly what I'm doing in my PhD. So I submitted it, and I got rejected. So I thought, okay. That conference had a little workshop called State in Programming Languages. And it was just like a one-day workshop where it didn't even have a formal proceedings. It was just like a technical report. And I thought, oh, well, I'll submit it there. I want to get some feedback. So I submitted it, got rejected. So I licked my wounds a bit and thought, well, maybe I'm not really a programming languages person after all. And I saw this conference called ICSM, the International Conference on Software Maintenance. And I thought, well, the kind of work I was doing, it was this technique, like slicing kind of technique, where you kind of delete lines of code to try and simplify the program. I thought, okay, that seems relevant to maintenance. So I'll submit it there, see what happens. That got rejected. So the referees' comments were at least a little bit more friendly. They kind of gave me some suggestions for improvement, whereas the programming languages one were actually quite offensive. I mean, they really did tell me to just not bother doing research. Forget it, mate. This isn't for you. But the software engineering community was a little bit more encouraging. And so I had another go in 1995. I thought, okay, I'll take the referees' comments and improve the paper, and it got rejected. So ICSM had a little workshop, not very prestigious, nothing kind of big, mainstream kind of conference. But I thought, well, I'll give it a go there. And it was a workshop on program comprehension. So this is now 5 full years after I published my thesis, and I haven't yet got a single paper. And finally, at IWPC, my paper was accepted. Hooray! And I was like, really, obviously I was quite delighted. So my message to PhD students in the audience is that there's no such thing as a rejected paper. If you believe in your work, then in the end, it will get accepted. And really, it's not rejected, it's just not yet accepted. There are such, if you don't submit it, if you give up, then it'll be rejected. But you're the one who ultimately decides to reject your paper. So if you believe in your work, keep on, and good things will come out of publishing it in the end. So as Aaron said, that much later on, if we wind forward another decade, I became very interested in the way computational search techniques can help with software engineering. And I'm very generously credited by some as founding this field, but I want to call out that many people worked on these ideas all around the same time as me. I happened to coin the phrase, and I pushed very hard for this agenda, but I certainly wasn't the only one. And the idea is very simple. We take search-based optimization. So think of that as any kind of computational search technique where you can have a large search space, too large to enumerate, and you instead of enumerating, you use a fitness function to guide you in the search in that space. At the intersection between that and software engineering problems is this area called search-based software engineering. The thing that was so surprising about it was just how generally applicable it was, how many software engineering problems would submit to this formulation. And this led to a really rapid increase in the number of papers in the topic. The growth curve fitted a quartic, and it's still growing to this day. And what I want to talk about in today's talk is how we can use some of these techniques in software testing. And if you're interested in the background to this, there is a survey paper I wrote with some colleagues for a keynote at ICST, one of the conferences. So it's this paper here, Achievements, Open Problems and Challenges for Search-Based Software Testing. And many of the challenges outlined in that paper from 2015 are still open. So there's still plenty of PhD material for people if you're interested. So if we take a step back, you can think testing is really all about searching. You search for test cases to reveal bugs, and the space of all possible tests is enormous, and you can possibly enumerate. And you want to be guided by a fitness function that's going to make it a limited amount of test effort you have more likely to reveal bugs. So we could be searching for test cases. We could also be searching for the test application order, because there might be more optimal orders in which to apply tests. So we can also search for patches to fix the bugs we find with tests. So this concept of search is a very general one in software engineering and in software testing. So in particular, in 2016, I worked with some colleagues to really drill down and try and turn this into something that could work in practice. And so at the time, Android was really booming. I mean, it's still very popular, but smartphones were really taking over, and there are a lot of apps. And so I thought, okay, let's see if we can use search-based testing to test Android applications. And we had this paper at ISTA on a technique we called Sapiens. It was my PhD student Kerr Mao who wanted to call it Sapiens. My only contribution was to say it should have a Z, not an S. Otherwise, when people Googled it, they would not hit our paper. So the thing that really struck me about the results we got from this was we wanted to make it so that this technology wasn't just a research technology, but would apply out of the box to any APK file, any Android application file. So we didn't assume anything. It was completely black box. We didn't assume anything about the source code. Well, we wanted to literally be able to just plug in a phone and run our test-based generation and find bugs. And so given that we had managed to do that, we thought, well, a great way to evaluate how good it is to apply it to the top 500 Google Play apps at the time. And what I expected to happen was that we wouldn't find many bugs, because I thought, well, the top 500 are going to be like pretty well written, and like a technology like this where it's kind of just searching, and hoping. And we can go into the details about the search in the questions, but I wasn't optimistic that we'd find lots. But actually, not only did we find lots, but we found them in every single category of applications in the App Store, and non-trivial numbers. And also, there wasn't really a pattern. It wasn't as if, like, I thought, well, maybe as they get less popular, they'll have more bugs in because they've just been less well tested by people. But that didn't happen either. So it really made me think, now what we've got in our hands here is not just a research paper, but we've got a technology on which we could make a company, because it will find bugs, and many companies can't afford to do testing. And so they'll pay us to do it for them, and we've got automation so we can do it cheaply. So we founded this company called Magica. The name's a little bit interesting. We wanted to have a name that sort of played into that Arthur C. Clarke statement that any sufficiently advanced technology is indistinguishable from magic. And we also wanted to bind our names into it. So the MA is from Mark, and the JI is from Jer, which is one of my colleagues, his surname, and the KE is Kerr, which is Kerr Mao's first name. So it's got all our names in, which was sweet. But it turns out that when I looked on Companies House, which is the UK registration of companies, there were 36 other companies that also had the idea of making their company name allude to Arthur C. Clarke and magic and magical. So I had to stick another arbitrary constant in there to make it a unique name for the company. So that's where the C came from. So yeah, no new ideas under the sun. Anyway, it turned out that we didn't end up helping lots of small companies who can't afford testing as we planned. What actually happened was the very first company we tried to approach was Facebook. And instead of saying, yes, we'll pay you to do some testing for us, they said, well, why don't we acquire your company? It'll be a lot faster and more efficient, and then you can develop it at scale inside Facebook. And so that was quite an exciting and exhilarating experience, but sort of daunting as well at the same time, because I'd imagined we'd have years to build up our company and learn a lot by doing, but instead we're thrown straight in at the deep end. Within 6 months of founding the company, we'd given up our day jobs, and the three of us were working at Facebook. So that kicked off a process at Facebook of developing automated testing technology. So Sapiens paper was 2016, we acquired and started at Facebook in February 2017. And this led to what's now become an agenda in the company of using simulation to achieve testing goals. So we have this web-enabled simulation project starting in 2019. The goal there was to simulate all of the user community on the platform, but not to simulate the platform itself. So we simulate the user community as bots, and they interact with each other. But when one of the bots sends a message to another bot, it goes through the same call stack as when you or I would message each other. And we got a paper on that in 2020. In 2020, also at the same time, Sapiens had evolved into a technology called Virtual Alpha, which was like, Alpha is our alpha release. So it's initial dog fooding of our products with real users. But what Virtual Alpha was about making a virtual community to simulate that real community. So we can have much earlier signal, and we can do many more things in simulation that we can't do in practice. And then in 2021, we developed a metamorphic approach, which grew into this tool called MIA. And that's been used a lot for finding issues in what we call integrity, which essentially is user safety. So I'm going to talk a little bit more about this in detail in a minute, but the top line here is that people have been horrible to each other since we came out of the caves, and possibly before. And software technology allows people to be horrible to each other in new ways, all sorts of ways. And all of the bad things that can happen on platforms, software platforms like bullying and harassment and hate speech and threats of violence, all these nasty things that people do to each other. We have to have technologies to detect those and prevent them. And if that's the case, then we have to have technologies that can allow us to test those. And so the simulation platform that we built turned out to be the ideal platform for that, because we can simulate bad actors, we can simulate good actors, and we can simulate the interactions between them, and then we can check that the platform will actually behave correctly on this. So there's now a simulation-based testing team that's developing these ideas in the company. So I want to dig in a little bit and give you some of the sense of what all this plays out like, and how we use some of these research ideas, having given you some context on how I came to be there and the journey I've had. So one of the things that occurred to me when I joined the company, thrown in the deep end, as it was like, the scale is going to be a night, how on earth will our techniques won't scale? And the scale is large. Let me just give you some figures to kind of bound this. So that the number of people who use these products is currently over 3.5 billion. That's a lot. But in software engineering terms, what that means is there are over 100,000 commits to the repo every week. That's a commit every few minutes. So you'd expect that the technology wouldn't scale. It's been developed as a research project, but actually the surprising thing was the core technology does scale quite well, because although it's the case that, yes, you can have more and more commits being submitted, and now that the rate is much greater than 100,000 when I made these slides, but let's say 100,000 plus per week. But that as you get peak stress and there's more and more commits coming in, you can also scale up the response. So most companies like Facebook, Google is the same, Amazon, of course, have elastic cloud computing resources, and therefore they can easily scale a response so long as the underlying technology is parallelizable. And the lovely thing about these search-based techniques is they're embarrassingly parallel. So it turned out that the scalability challenge in terms of the technology being able to scale to the challenge of the rapid change in the software wasn't a problem. We were able to deploy it within months. And this is what the initial deployment looked like. What you're seeing here is a whole array of emulators running the Sapiens tool in parallel on the Facebook products as they looked in 2017. So I think the top line is maybe iOS Facebook. One of them is Messenger, I think. I'm not really sure which is which, but what's actually happening there is each one of those is an emulator. It's loading up a test user into the app, and then it's using the search algorithms to try and search through the GUI to try and find bugs in the app. So if you're interested in that early part of the journey where we deployed the research technology from research labs into the company, then there is a paper about that that was published in 2018. There's still some very interesting challenges that we talk about in that paper that haven't been tackled. So it's not as if it's a done deal. So as a PhD supervisor, I've been very fortunate to have some very good PhD students, and many of them have ended up in the company at Meta. So the two who I originally worked with and we formed the company Magica got acquired. Both those are still at Meta and are doing very well. And then next we hired Nadia Al-Shawam, with whom I'm actually working on a daily basis still today, and Alexandru Marginian, who I'm also working with on a daily basis. And maybe there'll be some more, who knows. So I wanted to just briefly focus on this chap, Alexandru Marginian, because while he was doing his PhD, he did an internship at Meta. And I said we thought scalability would be a challenge, and then it turns out not. This was a real eye-opener. He took the technology that he was working on for his PhD, which was all about transplantation, and he applied a very specific vertical of this to the problem of automated fixing. And he, in a 14-week PhD internship in the company, was able to take that, deploy it into this large CI infrastructure that's powered by elastic cloud resources and so on. And what on your laptop is just a PhD demonstration project suddenly became a scaled out technology for finding and fixing bugs. So the lovely thing is, once you've got an automated technology for finding bugs and you've got an automated technology for fixing bugs, you now have an end-to-end self-improvement cycle where software can essentially find and fix bugs in itself. Mm-hmm. And we deployed this and published some initial results on it. And the thing that I think is so lovely from a point of view of being a PhD student, doing an internship in a company like this, is the impact you can have for your PhD work. So I can't see everyone's hand, but if you could kind of, if you have any of these products on your phone, like Messenger, Facebook, Blue App, Instagram, actually WhatsApp as well, for that matter, then you are running software that is impacted by Alex's PhD. Specifically, you're running software that contains bug fixes, so patches that have been applied to the code, that were applied automatically by a technology that also automatically found those bugs using computational search. So you're running software that's been directly affected by his PhD internship. And I still find that gives me goosebumps, really, to think you could be a PhD student and then suddenly within a few months your ideas go from being something you try out on your laptop to write a paper to something that you can go on almost any journey on a public transport and look over and see people with phones in their hand that are running the software that your technology's created. I think that just really is quite an amazing experience. And therefore, if you're doing a PhD, actually, this is also true for master's students and bachelor students, I'd really encourage you to consider doing an internship in one of the tech sector companies. We're in a recession at the moment, so hiring is not so strong. But if you're doing a PhD, it's quite a long journey. Hopefully, we won't always be in that situation with the global economic situation. But even so, even in this situation, take every opportunity you can to try your ideas out in practice. I'll skip over the slide. I don't want to. Well, the paper that describes the work Alexandru did in his thesis was published at ICSIA a few years back. So if you're interested, you can read about it. I think SAPFIX is the only thing you need to put into Google to find the paper. So I want to spend 10 minutes now, so I will be slightly over the half-hour promise, just telling you a little bit about how we scale genetic improvement in this simulation-based testing approach. There is a paper about this, and I talk in that paper about this build effort problem, which, as I say, is the problem of if you're going to do computational search on software systems, each time you want to test what your test is achieving, you have to build the whole system and then run it. In order to run it, you have to build it. And so there's this build effort problem. And also, as a software engineer, you want to explore new features. But if you have to build the whole feature first, and then only to discover that maybe it has an interaction with some other feature, or to try and find the right parameters, that's also a real bottleneck on the design process. So what I'd like to focus on now is how we could tackle both those problems using a simulation-based approach, and in particular, this thing we call mechanism design. So by simulation, what I mean is we take Facebook infrastructure, by which I mean essentially the data stores and the processing elements, and on that infrastructure, on the real infrastructure, we deploy bots. And the actions that the bots perform and the observations the bots can make are exactly the same as the actions and observations you can make on the real infrastructure. And indeed, they go through the real infrastructure. So that means we can then reward these bots using things like reinforcement learning to behave in bad ways that we don't want to happen on the platform. And then we can look at ways to improve the platform to make them harder to achieve. Now, all the interactions that occur, of course, are between these dub bots. We call it dub because it's like a WW, because it's kind of cut down version of www. But it is the real dub infrastructure. Hundreds of millions of lines of code are being executed, but the bots are the thing that's being simulated. We have a paper that describes this if you want the details. But the kind of thing we want to tackle with this approach is harmful behaviors. So let's pick an example of one like when someone wants to scam or spam you, then they're going to use that social network to try and crawl over the network and try and find people that they could scam. So in this situation, what many companies do, ourselves included, is you focus on trying to detect this behavior. And if you detect that behavior, you want to prevent it. Wouldn't it be better if we could actually design the platform so that by design, it was harder to achieve that? So detection is where the sector is currently at, and the technologies for this are pretty impressive, I think, given that they have to scale and they have to use a lot of smart machine learning to detect these behaviors. But imagine if we could design the technology so that it prevents it at heart. So detection is a good technology, but any technology that can prevent is much better. So if you think about roads, in the UK, like the road network, we have speed cameras. This is what they look like, the yellow box on that. They paint them yellow like this because they want, although it's a detection technology, we want it to deter people from speeding. So we paint them quite yellow so you'll slow down when you see it. And the prevention technology for roads is not that great because we put these speed humps in the road, which don't really stop you speeding. If you do speed, it probably makes it that little bit more dangerous. And if you're not speeding, it still damages your car. So it's sort of bad in so many ways. And yet we still use them because it's the best we've got. But think about how that plays out in software. Software engineers are very, very fortunate engineers. We have this extraordinary engineering material that nobody else in the history of our species has worked with. This entirely virtual material. So when we do the virtual equivalent of putting speed humps into our software to make a prevention technology, we have the ability to make the virtual speed humps not harm normal users. So when you're not speeding, you don't get hurt. To make it very difficult for people to achieve their harmful ends. And to make it very subtle and nuanced, instead of being a great big lump of tarmac in the road, we can make it all sorts of little parameter tweaks and changes in the software. So how are we going to find that sweet spot of all these different parameters and things we're going to have to tune to make the software such that it's harder to do the bad thing, but not hard to do the good thing? So imagine we've got these bots and we're rewarding them for crawling. And we want to allow crawling, which is like, say, I'm a new person on the platform and I want to find all my friends, but I don't want to allow someone who's crawling the platform to try and find victims that they might want to scam or spam. Now, I could tweak the software itself and then run the bots and then see if the good ones are okay and the bad ones are impeded. The trouble is you can run into this build problem. If I'm going to tweak one of these back-end infrastructure parameters and then I have to rebuild the entire platform, that's not going to scale. Instead, because I'm running this as a simulation, I can have this simulation layer to simulate the effect of what these changes would be on the back-end infrastructure. So instead of actually changing the code, which is what traditional genetic improvement does, what we do is we expose a layer of parameters that correspond to product changes we could make, and then those act as the virtual equivalent of speed humps on the observations the bots can make and the actions they can perform. To make this more concrete, imagine it's like a constraint vector. This bot can only send 4 messages a minute. It can only read 12 messages a minute, and it has to leave a 17 millisecond gap between messages, say. And then this bot, different things for the same parameter, and then so on. Now, what's happening now is the bots are trying to achieve their goal. There may be good bots, or there may be bad bots, but they're trying to achieve their goal. But the constraint vector is experimenting in parallel with all sorts of different versions of our platform infrastructure that might tend to impede the bad guys and help or not impede the good guys. So, of course, in reality, this constraint vector is much, much bigger than the one I've drawn here. And it is essentially a search space. And we're searching for that tiny little sweet spot where these few little parameter tweaks here will tend to impede the bad behavior and allow good behavior. And so what we're doing essentially is we've got an enormous search space, and it's like searching for a needle in a haystack. But the good news here is this whole area called search-based software engineering is just about exactly that problem. How do you define techniques which will allow you to search large search spaces and find the needle in a haystack? So essentially what we're talking about is a combination of machine learning to train the bots to behave in ways that are interesting and important, simulation to simulate the user community and to simulate the changes we make to the product to attack this build effort problem, and computational search to search that simulated space of product changes to try and find those changes which will simultaneously meet 2 objectives: allow the normal users to go about their daily business, but impede people who have harmful effects that are trying to misuse the platform in ways it wasn't really designed. So essentially, this leads to what we might think of as a cyber digital twin of the Facebook platforms. What we've built is essentially a cyber digital twin. There's a huge amount of research on cyber physical digital twins, where you build a simulation of a real engineering system, like a chemical plant, for example, or a road network. And all we're doing is we're doing what we call a cyber digital twin. That has all sorts of interesting consequences in the digital twin space, which I'd love to go into, but I want to go to questions. So I'm going to resist the temptation to do that. And instead, if you're interested in that area, I point you to this paper. Just to whet your appetite a bit, we essentially can have a hierarchy of digital twins where each one is a simulation of the one below it in the hierarchy. And that allows us to do an engineering trade-off between the computational time required to get simulation results and the fidelity of those results to the underlying thing they're trying to simulate. That's not possible with cyber physical digital twins. And it's something that's unique, once again, because we're software engineers and because the thing that we're simulating is written in the same engineering material as the thing it's simulating that allows us to have this property. And ultimately, it would allow us to actually have a self-applicable loop, which I just think is, got tremendous potential. We're just at the beginning of exploring this right now. So I hope that's given you enough of an overview to see the kinds of things we're doing with simulation, with computational search, and with testing in the company. And therefore, I'd like to shut up now and listen to you a bit and hear your questions. And either feel free to paste them into chat or put your hand up and ask them out, however you prefer.
Yes, sir. The title of your paper is Software Engineering for Reliability and Safety, right? What objective measure are you using for reliability and safety?
Thanks. I didn't know that was the title of the paper, but that is the correct characterization of what we want to do. So the reliability work is somewhat separate from the safety work. So let me take the reliability work first of all. So the reliability work, what we're really after there is the kinds of things which happen to the app in your hand that would make it unreliable for you. So if it crashes, if it's out of memory, if it just doesn't respond. The nice thing about all of those properties is they're what's known in testing circles as an implicit oracle. I don't need to know what the correct output should be for the corresponding input stimulation I give to the app. I know it should never crash. So from a point of view of automation, that means that I can automate the process of searching for all sorts of scenarios. That's essentially the search space we're searching over. And then in order to determine whether the software's function correctly in those scenarios, I just use this implicit oracle, shouldn't crash. What's more tricky is to go beyond reliability and say, well, what should it do? Maybe it prints 42, it should have printed 17, not be a bit parochial. That's harder. That requires you to actually infer an oracle and understand what the software should be doing. Maybe new technologies will allow us to tackle that problem. But what we've been focusing on in our work on reliability is this implicit oracle. So the guidance is all about guiding to try and cover the search space of inputs as widely as possible. And the measure of whether you're actually doing any good as a tester is whether you're revealing these kind of input scenarios that can lead to crashings. Yeah, I hope that answers the first part of your question. And the second part was about safety. What is the requirement there? Now, with the safety work, what we've tended to do there is make a much more scripted approach. So whereas Sapiens will search that input space automatically, with safety, we've currently what we're working on is the process of allowing the user to define these scenarios in a simulation language, which involve different kinds of actors. So in most testing, you have this idea of a test user if you're doing an end-to-end test, and you log in as the test user, and then you see where they can have a bad experience. So from a reliability perspective, if the app crashes, it's bad experience. It's bad for every user, and you don't really need to think much about what this user is. It's just any old account, But in safety testing, you now need to think about three players. You've got a user here who's got bad intentions. You've got an innocent user here who's the victim of those bad intentions, and you've got the platform. And the platform might be functioning perfectly. In fact, from the bad user's point of view, the more perfect, more performant the platform, the better. Because this bad user is going to misuse that platform to try and hurt this person. So now in that kind of testing scenario, you need the ability to get into this world of, well, what do we mean by a test user in this test case? So that fits simulation very well. And we tend to do that in a scripted way. But we have just had a paper accepted for this next year's ICSI, where we talk about how we can scale that up using inference of tests. I hope that answered your question. It felt like it had a couple of parts to it.
That was great. Are you employing any machine learning in any of your models?
Yes. So in the safety work, in order to we can actually just specify specific behavior that we want to detect, like things that are egregiously wrong that shouldn't be allowed to happen. But we also want to be able to get ahead of the game. So we've experimented with things like imitation learning, where we say, well, we don't want to be too prescriptive. We just want to know anything that behaves in this bad way, which we can train. And we've also experimented with reinforcement learning, where we're thinking, well, maybe it'd be even better if we could just stand back and just define what badness is, and then not even say how to achieve it, but just let the bots try and achieve bad things and see if we can, our platform can detect those. Yeah, so we use machine learning to train the bot behaviors, but one of the interesting things is even a rule-based approach is pretty effective, we've found. So like we can just define rules that capture styles of behavior that we know are essentially characterizing bad actors. And the nice thing about that is very reproducible and deterministic, whereas once we use these more sexy sort of machine learning techniques, we can have problems with like reproducibility, which is very important for testing.
Right. Mark, I have a question here. So here's what I understand. So classic testing, like if you just use testing in the broader sense, you have to generate an input, you need to have an expectation, and then you check whether the input output actual thing matches the expectation. In this narrow particular class of testing, you are looking at reliability. The notion of expectation is defined in terms of some extrinsic capability, things that are independent of the program. Yes. So the program crashes and so on. And when it comes to safety, how do you define the sort of expected or behavior? Is that?
Well, that's one of the reasons why we need to make that a bit more scripted, because we need to say what, like we have to simulate the various actors in the story. Like one of the actors might be law enforcement, because ultimately we might need to, to take action, if there's something really, bad going on. So in the real world, so for those, you want to actually, you do want the oracle. You have to have assertions which assert this, in this scenario that I've just followed, where this bot does this and that bot responds in that way. No, this bot posts something that this bot claims is hate speech.
Sure.
That flags up a task. So now that has to be considered initially by some ML, which says, okay, it passes that. And then that might go to a human who finally says yes. And then there has to be an action, which is this gets taken down. And it has to happen within a well-defined time frame. So that's all scripted out as a kind of specific test case. The only difference between that and the way you might script out a test case, say in JUnits to test your Java program, is that you've got these different actors and they have different roles, and that's kind of important in this scenario.
Now, in your case, you have several layers of program. You have the apps, and you have the infrastructure, and whatever else might be there. So you're testing the apps in this case, am I right?
Well,
the reliability you're
in
testing.
Sapiens work, we test through the GUI, so that's testing mostly the client side. So it's the app, but of course the app then has to communicate with the back end stuff, and so it's sort of by extension it tests the back end, but it's not great at achieving coverage in the back end because it's actually doing it through the GUI. With descriptive work on the safety side, we're not really interested in the GUI that much, right? We're more concerned with the back-end systems that are classifying the various different kinds of content and so on, and how they interact with the overall software engineering workflow. So we dispense with the GUI and go straight in at the server side for that testing.
And the reliability, you worry about coverage, I assume, as in all paths, your classic fuzzing sort of thing. You create data that you have to drive through all of the paths and stuff, right? That's
right. Yeah, there's various algorithms that we use. Some are inspired by search-based techniques in the papers that I mentioned, and others are like more modeling based to try and generate a model of the GUI. GUI testing is actually a lot harder than you might think, because things can move around on the screen. You've still got to try and be able to stimulate the app to do them. There's lots of non-determinism, so you get kind of, which translates as flaky tests. There's all sorts of timing effects. So yeah, there's quite a lot of, we've played with all sorts of different algorithms there, and there's still plenty more to be done on that side of things as well. But yeah, one of the ultimate goals there is achieving coverage. Yeah.
There's a person raising hand. Aladdin, I will give you the floor.
Hi. Hi, doctor. Actually, I want to ask about something just you mentioned, about detecting vulnerabilities with rule-based techniques. Applying rule-based techniques, do you think it is scalable in the long run if you just reach a lot of users?
So I want to clarify, when I said rule-based techniques there, what I mean is, in order to define the behavior of the bots which are simulating the real users, we can use rule-based approaches. So if we use imitation learning to imitate the behavior of a bad actor, if it genuinely faithfully imitated the bad actor, most of its time it would actually be behaving normally, because most bad actors don't just spend their entire time being evil, nasty people. They do it a little bit on the side, So it's useful to be able to distill the bad behavior, put it into a rule-based system, and now you can dial up how bad is this. And the reason that's useful from a search point of view is, imagine you're searching the space of product improvements that are supposed to tackle this bad behavior. What you want to do is you want to have a really quick fitness evaluation that's going to dispense with candidates which aren't even, they're non-starters, right? So what you can do is you can dial up this bad behavior such that this bot is behaving so badly, if you can't prevent that, game over. Don't even consider it any further, right? So rather than using sophisticated techniques in that scenario, rather than using sophisticated techniques like imitation learning to imitate real users, what you actually want is an unreal user who's like like some kind of freak bad user you've made. So now any technique that can't stop that gets thrown away immediately, and you go on to the next level. Now you can dial down the badness a little bit and see if you can get through that, and now only finally, once you've done all that, you could use more smart techniques like imitation learning. So in that sense, the rule-based approach allows us to the bots essentially are there to act as a training guide for the fitness function that defines whether the product improvements that we're searching, the space of product improvements, are good. And so what you want is quick, good fitness. And so rule-based approaches to define the behavior is good there. Yeah, I think that's, I finally got there. That's what I was trying to say.
I have another question, which is about finding bugs in like search-based techniques. Like the finding bugs is always correlated with output, or just when I want to find bugs, usually should I look for the output, or with this technique, like you in your works, you guys just look for outputs to see the bugs, or you need to just inspect the behind logic of each software to understand if there's a bug or not?
Not sure I understand the question, but let me put it back to you and see if I got it. So are you asking are we only looking at what the user sees, or are we looking at internal states that the software might go through? This internal state fails some assertions, so things don't look good. But if the user doesn't see anything bad, maybe it's okay, sort of thing. So we tend to focus. I mean, all bugs matter, but some matter more than others, right? And so if we're going to bug a developer, we're going to irritate a developer by saying, hey, you need to go back and think about this, or you can't land your change until you fix this thing. We probably need to be, they're more likely to pay attention to us if we can show that this does correspond to something that's going to affect an end user. And in particular, we might even want to measure the severity of that, which we can do because we've got this simulation. So we can simulate how many users would be affected by this bug. So that's kind of nice. You get for free a kind of severity indicator, which is something, we've been stumbling around in the research community for ages trying around this problem, and most papers just treat all bugs as the same, and that kind of doesn't really work in practice, because you could be a purist like this. I'm sure Dijkstra would be turning on his grave the idea you could have software with bugs in it, but we're all using software with bugs in it every day of our lives, right? I mean, you can't. There's no software worth its. There's no non-trivial software out there that doesn't have some bugs in, right? That doesn't exist. It's like there's no human that's perfect, it's quite important. I think this isn't anything to do with my company. It's like in any practical scenario for software testing, it's really important to be able to give a signal to the developer about the severity of the problem you've uncovered. Otherwise, what we describe in the paper is what we call pseudo false positives. It's like, yes, you find an issue, and the issue can happen in practice. So it's not a false positive, but it's a pseudo false positive if the developer ignores it. So it's a tough criteria for a testing algorithm, because you could actually find, you could deploy a technique in a scenario and find hundreds of bugs, and actually they're all pseudo false positives. So yeah, it's a bitter lesson actually, that a lot of people who have great techniques that are good at finding a specific class of bug. You know, it's like, well, more important to be able to give that signal of severity, I think. And I think this is something we don't consider enough in the research community, you know, but that's life, you know. I don't know if I answered your question. I think I ended up answering a question I made up myself.
No. That's great. Thank you, Doctor.
Mark, if no one else has a question, I have one here.
Are there any in chat? I see there's some chats. No, they're not questions. Okay, right.
Okay, so when classic testing, at least one of the major challenge that comes in creating inputs, random inputs, is creating syntactically, in some sense, syntactically correct input. Otherwise, things just you're just creating input that are useless. Now, in your case, it's not, the input is some sort of events, user
Yes.
event.
We completely brush away that issue.
So,
because anything that can happen we're at the glass level, you know, so it's like simulating clicks and gestures, so everything's valid. The interesting thing is, you may think, yeah, but you know, this could simulate someone who's got 15 fingers, right? That's surely not, because like you know, so surely that could lead to false positives, right? And actually, it turns out not. And here's where scale is on our side, because what we thought would happen is we're testing on emulators, not real devices. And we have this property that our test might actually run faster than any person could really do. So we thought, well, we're going to find all these false positives where in practice that doesn't happen. It just didn't happen. It just didn't happen. What happened was, on Android in particular, yes, you go faster than any human can, but some of these devices, Android is incredibly fragmented environment, and some of these devices are much slower than others. So you going really fast is a bit like a slow Android device with a normal speed human sort of thing. So and the fact that you might have 15 fingers is like, well, you know, my 4-year-old child might have grabbed my phone and started doing all this thing, and I still don't want it to be. I don't want to pick it up and find it's all crashed, you know. So what we found was even though it might be that the chance of this bug happening in practice is 0.001, if you multiply that by 2 billion people, you get quite a large number of affected users. So like anything we can find, even if it's very kind of corner casey, it does, you know, it is a true positive in the sense that it will happen in practice, and it does happen to some people. That's notwithstanding the answer I gave earlier on about, you know, the severity. Obviously, you still have to prioritize the order in which you're going to fix these bugs, and you would choose those that are most prevalent first. But yeah, so we didn't have the problem of like, are we generating invalid inputs, because everything's valid. And moreover, we didn't have the problem that even though they're valid syntactic inputs, that they might lead to a false positive outcome because like no real user could create that input. That didn't happen either, which is, you know, I wasn't expecting that.
So in these cases, how do you measure progression, whether you're creating test cases that are not really producing anything new?
That's a good question, because new here means, did you find a bug? I mean, if you didn't find a bug, it's not great. New can also mean within that, if you didn't find a bug, have you covered more? So that's very important. So we use feedback signal on coverage. And then even within coverage, you've got this, a lot of the algorithms we use essentially have some bias towards novelty, you know, essentially. So it's a bit like the algorithms that are trying to test these games, you know, like I was talking to some colleagues recently about the algorithms that are trying to test things like Minecraft, where I've never played Minecraft, so I may be talking nonsense, but my understanding is you have to get these crystals or something, or diamonds or whatever. But like, that's very rare. So like, if you make that your fitness function, you're going to have a plateau landscape with no fitness guidance. So once again, you have to kind of encourage novelty and have sub goals. And that's exactly what we do. So coverage is a great sub goal, you know, guide, and also novelty, seeing new things on the screen, you know, anything like that's good, you know. I'm not sure that was your question, but
yeah, sure. No, yeah, that's good. So, coverage is a classic measure, but I think in your case, the timing also probably plays a role, like you mentioned there. So there might be some, you know, certain things. I mean, you have events that are happening independently. A lot of entry points are independent on Android. You click here, there's not a linear flow. flow of programs. The way you select your events, the order of selection of events could change may they get the same coverage but different interaction.
Yeah, this creates a problem for replicability of the test. So, like, you may find a crash, but then if you do exactly the same sequence of events again, you kind of got lucky, and it doesn't happen the second time around. The nice thing here is that a crash is such a severe occurrence that a developer has to pay attention. So, in particular, if you imagine this is a technology you deploy just to go over the code base and find possible crashes, that's not going to be very actionable. But if every time a developer puts up a change, you run on that change, and furthermore, if you find a crash, you can show them a video of the emulator crashing, point to the line of code where it happens, which you can do from the stack trace. Now it's very actionable. So they don't really need now to be able to replicate your test in the traditional sense of like, I want to go and repro your test and try and understand and debug. It's like, no, at this line here, it can crash. Here's the proof. And usually because it's at a time when they've just submitted the change and it's very localized and it's got a video showing it crashes, they nearly always, we had about something like 75% fix rate. And the fix rate doesn't require them to be able to repro the test. I mean, some of them can be reproduced and that's useful, but it's kind of not essential, which is another interesting thing that I didn't expect. And is kind of, where we win once again. It's like an existential proof, and what I realized is, and this is another learning for the research community, really, for me, like in the research community, I think I want to evaluate my test techniques any good. I'll compare it against state of the art. I'll see, do I find more bugs on a code base? But when you then come to try and deploy that and give value to developers, what's much more important is whether you can interpose at the right point in the continuous integration with the right signal, localize it. Finding more bugs is one thing, but if you find them all in a kind of periodic deployment mode where you just give them a list of tasks and say, go and look at all these, that's, good luck with that. I mean, we have a paper where we talked about that approach and we got almost 0% fix rate, and so how you deploy as well as what you deploy makes a huge difference to whether you actually get things fixed.
I can see that if I push a commit and right away I get a feedback, hey, here it's failed, that I think temporarily, like I can make the connection much faster.
Exactly. And you've got to think this is all in code review as well. So like if the tool can comment before the code reviewer even gets to it, then when the code reviewer is going to say, did you look at the signal from the tool? Yeah. We used to do this thing. We used to collect the comments that the developers wrote, and they would actually talk to the tool. They'd say, "Oh, nice one, Sapiens." Yeah, and they'd say, "Did you see what Sapiens said about your diff? Maybe you need to go and check that." And so like it really felt like the tool was like a member of the team.
That's pretty cool. That's pretty cool. And how about the infrastructure itself? That is probably not a APK. I mean, I'm assuming the infrastructure, the thing that you're talking to, your clients, your apps are talking to infrastructure, right? What about the testing of that?
You mean the testing infrastructure or the product infrastructure?
I'm talking about the foundation, like your Facebook. Somewhere there's a databases, and
Oh yeah, there's a huge backend. There's hundreds of millions of lines of code, mostly written in Hack. Yeah.
What about the testing of that backend? So far, I assume you've been mostly talking about the front end and some interaction through the backend with the front end, right?
Yeah, well, so for Sapiens, it's mostly about client side. For server side, we have lots of testing technologies, but we don't have, like, for example, we use Jest end-to-end testing. For example, we use unit testing, just like all other companies. We have various static analysis techniques that try and find bugs in those. But Sapiens is purely about the client side. And the back-end stuff we've done in my team with this simulation-based approach is all about safety. So it's not about reliability on the back end, although it can be applied there as well.
But in safety, you are doing some sort of a simulation, like you said. You create, what if the system behaved like this, and then so you're creating a virtual layer which simulates what the server might do. And if the server made the decision, then what is the implication on safety, right?
That sort of thing, yeah.
Now, how do you ensure that once you find a right feature vector, how do you ensure that the server can actually deliver that?
Well, that's a that's a whole other problem moving from the simulation to the deployment. It's non-trivial, yeah, as you say. But it's a trade-off between, you know, the ability to explore that space quickly and find likely plausible candidates. Think of it as a filter, you know, that the simulation allows you to identify some plausible candidates and write parameter tunings for them to consider before you then now have to go on and actually do real experiments with like hard implementations. Yeah.
Sure, that's good. Now, I think it's already noon right now, so at least we probably bring the formal session to a close, and we can continue discussion. And if there's any other students, anyone else has questions, please feel free to stay around and ask questions. And otherwise, we can again thanks our speaker.
Thanks very much for having me.
I enjoyed it.
Pleasure to be in Lafayette, virtually, albeit.
Yeah, we're gonna have you back sometime again. That'd be cool.